Hey guys, today we are going to do a review lesson for what we learned on Monday's Delta Math assignment regarding limits approaching positive and negative infinity. So we're just going to kind of review some things, clarify some things, but also for one of the processes in particular, we are going to expand a bit on it. So please make sure you're watching this whole video. It should be short. Nothing too long. Okay, so again, we are talking today about how to evaluate limits as they approach positive and negative infinity. So as you learned on Monday, all the limits we've done up until this week, your x value was approaching some specific number. X approaching 1, x approaching 5, x approaching 10, and we would take that number and plug it in. Well, you can't really plug in infinity. I know in the Khan Academy videos, you could kind of do some estimating based on if it was a really, really big number or a really, really big negative number. So today I'm just going to talk more specifically about the rules when this occurs. All right, so moving on. There are 3 possible cases for when your limits are approaching infinity, okay? And it all has to do with comparing the degree of the numerator to the degree of the denominator. So when you are given a function, you're going to look at the highest exponent in the numerator and compare it to the highest exponent in the denominator. So the first option, as we have here, is when the degree of the numerator is less than. Remember it, please. This is the less than symbol. All right, if the degree of the numerator is less than the degree of the denominator, and we're going to use exactly what we used for our horizontal asymptote rules. I know it was a long time ago, but when we studied our rational functions where we would have a vertical asymptote and a horizontal asymptote, and then we'd have a graph here and a graph here. All right, I know that was back before Christmas break. It was a long time ago, but the way we found our horizontal asymptote over here, that's the same way that we find the limit to infinity if your degree of the numerator is less than the degree of the denominator. Because again, this asymptote is telling us what this function is doing as I go to the right or to the left forever. I'm getting closer and closer to that horizontal asymptote. And so pretty much the rule is it's always going to be 0. Okay? Always. No ifs, no exceptions. If the degree of the numerator is smaller than the degree of the denominator, your answer is always going to be 0. Whether it's positive infinity or negative infinity, that doesn't matter. All right? So example down here, evaluate the limit. Well, if you have the limit going to positive infinity, I see the degree in my numerator is 1. The degree in my denominator is a 2. Well, 1 is less than 2, so that means that my numerator degree is less than the denominator degree. No calculation has to be made. My answer is automatically 0. All right? That's it. That's all we have to do. And again, the reason that that's all I have to do is because the limit is approaching positive or negative infinity. If this instead was as x approaches 2, well, then we don't use this process. We use the plug-in process that we've done up until this point. But because specifically it's the limit as x approaches positive infinity or negative infinity, this is now my new answer because these are now the new rules that we're using. Okay? All right, let's move on to the second option for review. This one is if the degree of the numerator is equal to the degree of the denominator. Same thing. This is the same step we used for our horizontal asymptote rules. Okay, if you have the degree of the numerator equal to the degree of the denominator, you simply take the ratio of the leading coefficients. Okay, so you look at the term that has the highest exponent in the numerator, and you look at the term that has the highest exponent in the denominator. Be careful with this denominator, though. This is not just x squared. This is a negative x squared. All right, so the only 2 terms that I have to be worried about here are 9x squared in the numerator and negative x squared in the denominator. As you saw from the videos on Monday, these x squareds can just cancel. All right, so that leaves me with 9 divided by negative 1, which is negative 9. That is the ratio of the leading coefficients. That is the limit as you're approaching positive or negative infinity. Again, just because this limit was approaching negative infinity, even if I was approaching positive infinity, it would be the same answer. So what does this mean graphically? This means that if I was to graph the function all the way down here at -9, I actually have a horizontal asymptote. So whatever my function looks like, and I don't know exactly what it's going to look like, but whatever my function looks like, let's say looks something like this, both the positive, the right side and the left side are going to be approaching that y value of -9 as we go to the right forever towards positive infinity, and as we go to the left forever towards negative infinity. Okay? All right, moving on to our third and final option. This is the one that we have to clarify a little bit more from what you learned on Monday. So, if the degree of the numerator is greater than the degree of the denominator. Now, back when we did our rational functions, we didn't utilize this, all right? I kind of said, oh, we'll use this at a different time. You get something called a slant asymptote, where we were only dealing with horizontal asymptotes at the time. All right, now this includes polynomials as well. Polynomials do not have denominators, therefore the numerator is automatically greater than the denominator. Okay, now for these problems on Monday, you were told in your Delta Math assignment that if the limit was going to go to positive or negative infinity, if that was going to be the answer, you were going to write does not exist. All right, so that was specific to those problems. Now we're going to delve a little deeper to figure out, okay, well, would my answer have been positive infinity or negative infinity? Because that's one of the two options. All right, so in these examples, you are not writing does not exist for an answer. You are writing positive infinity or negative infinity. Now, for these questions, you're going to use our end behavior rules that we learned back when we were dealing with polynomials. So just a recap of those end behavior rules. We had to compare the degree, the leading coefficient in order to find the end behavior. So, excuse me, if we had an even degree and your leading coefficient was positive, that means your end behavior was up and up. All right, if your degree was even and your leading coefficient was negative, that means your end behavior would go down and down. If your degree was odd and your leading coefficient was positive, well, remember, the positive leading coefficient tells you the direction of the second arrow. Odd degree means they have to go in opposite directions, so you would have a down-up end behavior. And finally, if we had an odd degree and my leading coefficient was negative, again, a negative leading coefficient tells me the direction of the right-hand end behavior. Odd degree means they have to go in opposite directions. So these are the end behavior rules that we're going to utilize. Now, when we come up with these arrows, if that arrow is pointed up, do you think my answer is going to be positive infinity or negative infinity? Well, an arrow going up forever, yes, that means that my answer would be a positive infinity. If my answer is a down arrow, that means my answer would be a negative infinity. You're not going to have both arrows as your answer. You're only going to be utilizing one of them. And that is all dependent upon whether your x value is going to positive infinity or negative infinity. So let's get to our example. So we've got example 1 is the limit as x approaches infinity of 4x cubed minus 8x to the 5th. Now, when you first look at this, you might be thinking, okay, well, how can I compare the degree of the numerator to the degree of the denominator? There is no denominator. Well, if there's no denominator, that means your denominator is just 1. So that means that the highest degree in the numerator, which is a 5, that's the highest exponent, is automatically the biggest degree, okay? It's automatically bigger than the denominator. So this is the term that we're going to utilize, a negative 8x to the 5th. So my degree is 5, which is odd. My leading coefficient, and again, you have to be careful here, my leading coefficient of that term is not 8. It is a negative 8. So we've got an odd degree and a leading coefficient that is negative. That means my end behavior is going to be the up-down motion. But that's not my final answer, okay? Way back in polynomials, we would leave our answer like this because I wanted to know what's the end behavior. Well, my end behavior is up-down. But this is more specific. I'm not asking for the end behavior. I want to know what's the limit as x approaches infinity. Now, as x approaches infinity, that means as you go to the right forever. So we're going to come over here and look at the right-hand arrow. Okay, because if this end behavior is telling me I go up to the left and down to the right, well, I only care about this right side arrow if x is going to positive infinity. So that means as I go to the right forever, where is my function going? What y value is it approaching? It is approaching a y value of negative infinity. Okay, so don't get confused with the different infinities here. My x value is positive infinity. That just means I'm going to the right. But the answer to the question is based on if I'm going up or going down, which is also a positive infinity or a negative infinity. So again, going back to what we did on Monday was your answer here would have been does not exist because of the fact that it's going either up to infinity or down to negative infinity. We are now going a step beyond, so your answer is no longer does not exist. We are now being more specific with our answer, and that answer is negative infinity. That's where I'm heading. I'm going down to negative infinity. Okay, let's do the second example. It got cut off at the bottom of the page, so I just rewrote it over here. So example 2 is the limit as x approaches negative infinity of x minus 3x cubed over 2x. So this one now you can see a little bit easier that the degree in the numerator is a 3. The degree in the denominator is a 1. So 3 is greater than 1. So that's why we're doing this end behavioral process here, because the degree of the numerator is larger than the degree of the denominator. Okay, so we have to look at the entire term in the numerator with the highest degree, which is negative 3x cubed. And we take the entire term in the denominator with that highest degree, which is just 2x. And we have to simplify this. So negative 3 divided by 2, well, that doesn't really simplify. That's just negative 3 over 2. But x cubed divided by x to the first would leave us with an x squared. So you're not utilizing, this term or this term. You're utilizing them combined together, and you have to simplify. Okay? That's now where you could pull out your degree and leading coefficient. All right, so when you do this process of writing out your degree and leading coefficient, you're not going to be writing a 3 or a 1. You're going to be writing the simplified form of both, which is 2. So my degree is 2, which is an even number. My leading coefficient is a negative 3 over 2. So that means my end behavior is down and down. Now, if both our arrows are down, I automatically know that, okay, down means I'm going to negative infinity, so that's going to be my answer. But if the arrows are going in opposite directions, well, then again, we have to come back up here to the original problem and see, okay, which x value am I approaching, positive infinity or negative infinity? And that's going to tell me which arrow I look at. So if x is approaching negative infinity, that means I go to the left forever. So that means I'd be looking at this left side arrow. That left arrow is going down, down, down forever to negative infinity, and that's why that is our answer. Okay. All right, let's move on to just one final question, kind of like an exit question. I don't want to do too many examples because I know you did a bunch of these already on Monday, but this one's a little bit more difficult, okay? This one takes it up a notch, and so I just wanted to try it out, have everybody see what you get. Okay, so this is the limit as x approaches infinity, but now I have a lot of negative exponents, okay? I don't like those negative exponents. So what we want to do is we want to try and simplify this before we're pulling out the degree, leading coefficient, or, comparing anything. So what we're going to do is we are going to actually split up this fraction. So because there is only one term in the denominator, right, your denominator is a monomial, you can actually split this into two separate fractions. So now that you have the two separate fractions, you can actually divide and simplify. Well, when you divide two things with a common base, right, what do we do with the exponents? We subtract the exponents. So this term is actually going to be -2 minus -4. And then over here, we're going to subtract, we have -3 minus -4. Well, that does look a little confusing right now, but if we do a little keep change, -2 minus -4 becomes -2 plus +4, which is just x squared. Minus 3x to the -3 minus -4, do a little keep change. That's -3 plus 4. -3 plus 4 is a 1. So this very complicated problem here is really just the limit as x approaches infinity of x squared minus 3x to the first power. Well, now there is no denominator. My denominator is 1. So that means that my numerator is automatically greater than my denominator. So we have to come back and use our end behavior rules. So the term with the highest exponent is x squared. That has a degree of 2, which is even. My leading coefficient of that term is just a +1. So that means that my end behavior is up and up. So automatically I know my answer is going to be positive infinity since both arrows are going up. But just to make sure, again, we come back to the original problem, which says x is approaching positive infinity. If x is approaching positive infinity, that means that we're going to the right forever. So we are looking for the arrow, the end behavior that's going to the right, and that is up and up. Oh, it's up. All right, yes, it's up and up, but going to the right is just going up, which means that as you go to the right forever in this function, okay, you are going to be going up towards positive infinity, just like you would on the left-hand side too, okay? All right, guys, hope that was helpful. For your homework for this, please make sure that if you get to a situation where, like this one, where the degree of the numerator is greater than the degree of the denominator, your answer now should either be positive infinity or negative infinity. You should no longer be writing does not exist like you did on Monday. Okay? Hope you guys are all doing well. Let me know if you have any questions, and see you later.